Hi everyone. So this video is all about frequency distributions, expected value, and variance. And in this video, I'm going to tie together some of the topics I've said in other videos. So if you don't remember what a frequency distribution is, go see that video. If you don't remember what a standard deviation or variance means, go see that video. So here we go. So if you harken back to some of the stuff I've done on frequency distributions, what you remember is that frequency distributions are essentially a count. So you have a bunch of outcomes. If you do it in like a histogram way, you have outcomes that are bins and bin ranges. But an outcome could just be an outcome, you know, scoring a 0 on a test, scoring a 1 on a test, a 2, a 3, a 4, based on, GPA rules. So 4 being an A, a 3 being a B, a 2 being a C, and a 1 being a D, and a 0 being an F. So instead of bins, you can have an outcome. And then if we harken back to frequency distributions, there's usually a certain number of people in each outcome. So let's just call this F of X, or I'm just going to call this F for right now. And F in this case stands for frequency. So let's just say 18 people failed. 15 people got a 1, 25 people got a 2, 30 people got a 3, and 40 people got an A. And you remember from previous stuff that you can calculate something called a relative frequency. And to do that, you take the frequency that you have, in this case 18, and divide it by the total number of observations, which in this case is 128. I'm going to set E8 fixed. So $sign in front of the E, $sign in front of the 8, hit enter. And then I'm going to roll this formula down. All right. So you also be relatively familiar with this. This is frequency, and this is relative frequency. Now, I'm going to show you how expected value and variance is born off of this idea. This idea that, like histograms, like you have the bin, and in each case, the bin is no longer a range of values. The bin is actually a defined outcome, like you are getting a 0 on exam, you're getting a 1 on exam. You can think of these parts as bins. Similar to a histogram. You can build a frequency distribution off that histogram. And then you can calculate an expected value and variance based on like the real life phenomena of frequency and histograms. And I'm going to show you how to do that. So often in this kind of structure, you'll see it in your textbook represented in this way. What I'm going to do is I'm going to right click on this E. I'm going to click hide. And so what you'll be given often in the textbook is a set of outcomes and a relative frequency set. And I'm just going to round this to 2 decimals just to make it easy to understand for us. But point being, you've seen what's underneath all this now. And so now we're going to calculate what is called a expected value. And I'm going to prove to you that expected value is essentially your average. It's the same calculations as calculating a normal average. So to do it with frequency, you do x, your outcome, times your relative frequency, which I'm going to call just f of x. equals 0 times 0.14. And then this next one is 1 times 0.12, 2 times 0.2, 3 times 0.23, and 4 times 0.31. I'm just going to roll this formula down. As you can see, is D3 times F3. And because I have no dollar signs, it's just going to roll straight down when I copy it down. And then if you want to know the expected value, or average, or mean, I'm going to call it EX. You just take the sum of what you just calculated. So we're going to add up all of these values. We get 2.460938, or rounded to 2.46. Now, I have said that this is exactly the same math as an average. So you're just calculating the average value. And so what I want you to remember is underneath this 0.14, if I unearth the regular frequency, underneath this 0.14 is essentially the math of 18 over 128. So to write this out in another way, I'm going to use another sheet for this. And what I'm going to do is I'm going to copy this frequency distribution and write it in a different way. Instead of relative frequency, I'm going to actually remove this. And I'm going to write the fraction. Remember we did frequency divided by the total to get relative frequency? So this cell is really 18 divided by 128. And notice how this is the way that's often done in your textbook. You're just multiplying the outcome by the relative frequency to get the number, and then you're adding them all up and getting the expected value. This is the way in the textbook broken down for you a little bit more. And so I'm going to continue writing down all these frequencies in fraction form, so you can really see what's underneath it. Now, one point I want to stress is that what is really going on is you have 128 total values. I'm going to highlight that. And I'm going to draw highlight. And I'm going to highlight that 18 of those 128 values are zeros. 15 of those 128 values are ones. 25 of those 128 values are twos. 30 of those 128 values are threes. And 40 of those 128 values are fours. That's what's really going on, both in what you see in your normal statistics textbooks and just sort of the math itself. You're typically, in sort of the textbook way, essentially multiplying the outcome by a fraction. So this is the sort of underground math, underneath math that's going on. And so what this ends up being is 18 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 18 zeros in your data set. There are 15 ones in your data set. There are 25 twos in your data set. There are 33s in your data set. And there are 44s in your data set. And all that's happening when you calculate that expected value from frequencies is you're finding the average of a data set that looks like this, where you have 18 zeros right here. You have 15 ones. You have 25 twos. You have 33s. And you have 44s. Given your frequencies, it's not going to always be exactly this because you could have a different data set than I do. I made this up from the back of my head, but you could have different data. But this is sort of the mathematical concept here. And notice how we got 2.46 approximately when we did the average there, the expected value. If we do equals average, and we just highlight all this, an average should ignore the blanks. So it's in parentheses. We get 2.46 again. So instead of doing x times f of x, I just said, okay, what this really is a relative frequency. You already know what that means. That has a frequency underneath it. That frequency is essentially saying you have a data set with 18 zeros, 15 ones, and so forth. So I've proven that expected value is really just your mean. How you would figure this out if you didn't have a frequency distribution underneath it is you could just assume kind of the same thing we did here with the underneath math and say, okay, with, for example, 18,128, it's about 14%. So we could assume that this relative frequency is really, really close to 14 over 100, which means that out of 100 values, approximately 14 of them are zeros. And then you can do the same thing here like I did. Take the average. All right, now let's talk about variance. So if you're harking back to my last videos, variance is essentially the distance that an observation has from its mean. So you need a couple of things to take this kind of frequency distribution and calculate the variance. First, you need the expected value or mean. And I'm just going to take this one from our previous work here, and I'm going to copy it into this new folder. And I can also do the math again. Remember, it's outcome times relative frequency. Then you just add it all up. And then you take the sum of everything you just multiplied. I should get the same thing. Now I have the mean. Because remember I said variance is distance from the mean? That's sort of part and parcel of its definition. Now I'm going to do the exact same definition that I showed you in that video, which is variance is the sum of each individual value and its distance from the mean squared, and then we're taking the average of it. So in this case, it's n or n minus 1. And what I want you to see when we do this is we're doing the same thing with the math in this frequency distribution. So let's do it. First, we need to take the distance of the observation or its outcome from its mean. We need to take its deviation. So X stands for outcome. Just like an outcome on an exam is, you know, getting a F. A 0 stands for getting an F. And we happen to have 18 of them. So when we do X minus M, which is mu, which is mean, means your average. Some people might see that as a U if you see the Greek letter. Depends on how clear the textbook is. But when we do this, we're taking the deviation of just one of these to begin with. So 0 minus the mean, which is EX, which is this 2.46 down here. We're just going to do one of these to begin with. We're not doing all of them yet. We're just doing one deviation. That's this middle part right here. And we're going to find, since we have 18 of these one deviations, and 15 of these one deviations, and 25 of these one deviations, we got to find all the different deviations that we actually have. Because remember, it's just going to be underneath kind of with this the same number. It's 18 negative 2.46s. It's 30 0.539s. It's that kind of thing. Now, if you remember the definition of variance, we have to take the square of it because we need to remove the direction component of variance. So that's what we're going to do with, large this, see this caret right here? That's taking the square. Just like it says to do in our definition of variance, just like it says to do in the formula there. And I'm going to also put like an equals variance. So you know what that formula is equal to. And this is particularly the population variance. And so if you remember, we have to remove the direction. So we're going to take our deviation and we're going to take out its direction to the square. I'm going to pull that down. So now, I'm going to highlight this in a different color now. Now we've accomplished what's in orange. We've taken the deviation for a single observation, for a single outcome, a single 0. We've squared it. Now guess what? We have to do the sum. We have to add up all the deviations of all the observations in our sample. So what I want you to hearken back to when you think about this is that taking the sum is exactly the same thing as if we multiplied by relative frequency. So let me show you why. We're going to bring over relative frequency over here. And I'm going to give myself more space so I can continue this table. And we're going to sum them. So I'm going to call relative frequency f of x. And I'm just going to take the sum, f of x. And we take the sum by doing f of x times x minus mu to the second. So it's g times h is what we're doing here. And we're going to finish this off by just dragging the formula down. Now, what I want you to remember is that this f of x right here, if you look back here, it's really 18 over 128. So when we take the deviance, and I'm just going to say 6, I'm going to round it for you to use. And we do it by, we multiply it by the frequency, 18 over 128. What we're really getting in the underneath math is we're getting some number over total observations. And these total observations are essentially your big N. And now, remember that, first of all, this number represents 18 versions of that 6.056, of that deviance, of that square deviation. It represents 18 versions of that over the total number of observations. So we've summed 18 versions of that first observation just by multiplying it together. We've summed, did this part, and did this part for 0 right now, just by doing this math. And then by doing it across all the possible observations, we've summed it for each individual observation by itself. Now, here's what I want to show you. So each of these becomes some number that represents the total deviance of that outcome, sort of across 18 times n, over n, I mean, which is the total number of observations. When you add all those together, so you do that once, that twice, I think I have it 5 times. I'm not going to do all of them 5 times. I'm just going to do them twice. If you remember your rules of fractions from algebra and sort of high school, this does not become some number over 2n, for example. You don't add these n's together and get 2n. You have a common denominator. So when you add fractions with a common denominator, what really just happens is this n remains n, remains the same. So what's going on as we sum these down here in this way is we're taking the outcome, the square deviance, adding it 18 times, and then total observation stays the same on the denominator all the way down. And so we get here, when we add it all up together, some number that represents the average total squared deviation from the mean, which is exactly our definition over here for variance. And it's because as you sum these down, the common denominator 128 stays the same. And the numerator just keeps getting bigger and bigger and bigger because you're adding together sort of like values. You're adding together the deviance 18 times, the deviance 15 times, deviance 25 times, and so forth. So this 1.95 number is your variance. And then to take its standard deviation, remember from previous videos, it's just the root of the variance. So standard deviation is just going to be the square root of that 1.95 number. So now we've discussed expected value, variance, and standard deviation, and how to get that all from a frequency distribution. I hope this was helpful, and please let me know if you have any questions. Thanks, bye.